There's an FBI.
All right. Okay, so today we are going to move on to 10.4. This section, it's not too bad. I think this one's definitely a little bit easier than what we've been doing, those area problems. I plan on spending 2 days on this, and after going through the notes, we are going to do a soccer game tomorrow, but it's going to be 10.3 and 10.4, so a little bit more practice over the area of regular polygons that we did yesterday, and then a lot of what we're doing today. So today we're talking about perimeter and area of similar figures. Now, we actually skipped the chapter that talked about similar figures, but what you need to know is kind of the simple part, that similar figures, or two figures, they have the same shape but not necessarily the same size. So similar figures, if you look at their corresponding angles, their angles are going to be congruent. But what's important for what we're doing today is their corresponding side lengths are proportional. So what that means is that if you take this left side on the blue rectangle and write it as a ratio to this left side on the green triangle, it'd be 2 to 4. And if you reduce that, you get 1 over 2. So the ratio 1 to 2, that ratio from this side length to this side length is always going to be 1 to 2. Meaning this rectangle is always going to be twice as big. Okay? And you can see that by looking at the bottom. 4 to 8. See how if you reduce 4 over 8, you get 1 to 2, or right, same thing, twice as big. Okay? What we're talking about today is what happens when you take these similar figures. What would happen if you looked at their perimeter? Would it still be proportional, or what would the relationship there be? And it turns out that if you look at what's called the scale factor, that 2 to 4 reduced down to 1 over 2, okay? That's called the scale factor. So if the scale factor is A over B, whatever it is, okay, so A to B, then the perimeter is also going to be A over B, which makes sense because for perimeter, you're going to add all the sides. And then for this perimeter, you're going to add all the sides. So you're just, right, adding all of these sides that are proportional. So it kind of makes sense that the scale factor and the perimeter, they're going to be the same proportion. Okay? Now, to like prove it to you guys here, we said that the scale factor here is 1 to 2. So if I find the perimeter should reduce down to 1 to 2. So if I wanted to find the perimeter of this blue rectangle, add all of the sides. We do 2 plus 2 plus 4 plus 4. We get 12, right? And if I found the perimeter of the green rectangle, 8 plus 8, 4 plus 4, you get 24. So if you did 12 over 24, see how it's the same? Okay, so the scale factor and the perimeter are going to have the same ratio. Okay, so once you know one, you know the perimeter is going to be the same. Now the area isn't quite as straightforward, but it's similar. So if the scale factor is A over B, 1 over 2, the ratio of the areas is going to be A squared over B squared, which kind of makes sense because, right, to take area, which you multiply, right? So, to show you that this works, if I were to find the area here, 2 times 4, the area of that rectangle is 8. And if I wanted to find the area of this rectangle, we would do 4 times 8, and we get 32. So how this works is if you were to write this as a ratio, if you were to take 8 over 32, and if you reduce that, you would get 1 over 4, which, if we look at the other ratio, the 1 to 2, 1 squared, 2 squared, it all works, okay? Now, we're going to do a couple of different things with this today. All of them are pretty simple, but the first thing we're going to do is just practice writing these ratios. So we want to find the ratio of the smaller to the larger. So a ratio is the comparison of two numbers. So I want to find the ratio of the perimeters and the areas. Now the great thing about this is that we don't actually have to find the perimeter. We don't actually have to find the area because we already know that if I find the scale factor, if I know that these if I know that these trapezoids are similar, if I can find the scale factor, this side length to this side length, I can then find the ratio of their perimeters and I can find the ratio of their areas. So the first thing we want to do is we want to find the scale factor. Now, you have to read the directions here. Okay, it says find the ratios of the smaller to the larger, which means if you're going to write the ratio as a fraction, the smaller side length needs to go in the numerator, the larger side length needs to go in the denominator. So the smaller, 6, to the larger, 9. Now keep in mind that they have to be corresponding sides, so notice they're both the tops of the trapezoids to correspond. Now, big thing today, this is going to be the biggest thing today, you definitely want to make sure you reduce. You don't want to leave this as 6 over 9. If I divide each of these by 3, we would get 2/3. So the scale factor is 2 to 3. Knowing that, if I knew one of the other side lengths in either one of these, I could find the other side lengths in the other trapezoid because that ratio it's always going to be proportional like that. Okay? So if I wanted to find the ratio of the perimeter, this is really easy to do because once you find the scale factor, it's the same. It's also 2/3. 2 to 3. The area isn't much harder. You take that scale factor 2 to 3 and you square the numerator and square the denominator. So the ratio of their areas is going to be 4 to 9. So that's one of the things you're going to be doing today, but now to actually put this to use, because it kind of just seems like we're doing math for the fun of it, which is totally fun, but to kind of put this to use, we can use this idea to find areas, okay? So I have these two pentagons here. It tells me the area of the smaller regular pentagon is about 27.5, not exactly, but it's about 27.5 centimeters squared. If I want to find the approximation of the area for the larger regular pentagon, okay, so these are similar. If we wanted to apply what we did yesterday and the day before, if I wanted to find the area of this, oh my gosh, think of what I'd have to do. I have to find the apothem, right, because I can find the perimeter, but I'd have to find the apothem, and here's the thing. I'll take 360 divided by 5, that's not going to give me one of those special right triangles. Okay, it's going to give me a different angle. So I'm going to have to use sine, cosine, or tangent, remember all of that stuff to how to do that to find the apothem, and then I have to plug it into the formula. We'd have to go through all of that process. We don't have to do that because I know that these are similar. So what I can do is I can first find the scale factor. Now, on the one above, it said write the ratio from smaller to larger. Unless it specifies, it really doesn't matter which one you do first, as long as you stay consistent. So if I want to write all of my ratios as smaller to larger, that's fine, but they all need to be written as smaller to larger, no matter what I'm talking about. If you want to be a rebel and do larger and smaller, fine, but you just need to stay consistent through the whole problem. I kind of just like to do the first one over the second one, just for consistency purposes. So if I want to find the scale factor, it would be 4 to 10. And then, of course, we want to reduce, which would give me 2 to 5. Now, that's the scale factor, which means all of the side lengths are in this ratio. And actually, it doesn't really matter for this one. The perimeter is also in this ratio. What I'm talking about, though, is area. So this is not the ratio of their areas, okay? The ratio of their areas is 2 squared over 5 squared, which is 4 over 25, 4 to 25. Okay, here's what we're going to do with this. I have this ratio 4 to 25, which means the smaller pentagon, okay, if I were to write the area of the smaller pentagon over the area of the larger pentagon, and I were to reduce it down, I would get 4 over 25. Okay? What we're going to do is we're going to set up a proportion. Because the area of the smaller to the larger is always going to equal 4 over 25. But this is where I said you have to stay consistent. It needs to be smaller over larger. So over on the right-hand side, I need to write the areas of the smaller to the larger. But I only know one of these. I only know the area of the smaller one. So in the numerator, we're going to write 27.5. And what I'm looking for is I'm looking for the area of the larger. So that's where your variables can go. Okay, so we have this proportion set up. Does anyone remember how to solve a proportion? Leo?
You multiply the denominator by the opposite numerator, and
Yes.
then same thing with the other one.
And they're equal to each other. So these are both cross products. So I would take x times 4, which is 4x. I would take 25 times 27.5, which gives me 687.5. Those are equal. Cross products are always equal. And then if I divide by 4, you get about 172 centimeters squared. So notice, I can avoid all of that sine, cosine, finding the apostrophe, all of that, because they're similar. I know they're similar, so if I know the area of one, I can find the area of the other. Okay, questions on those? Okay, let's get this included to page 37. This is section 10.4. It is perimeters and areas of similar figures. All right, so we're going to start knowing that the figures are similar. We want to compare the first to the second, and we are going to get the ratio of their perimeters and of their areas. So first one, we're going to have two right triangles. Okay, they tell me that they are similar, so I already know that the corresponding sides are all proportional, which means if you take this side length over this side length, it would be equal to the bottom over the bottom, which would be equal to the hypotenuse over the hypotenuse once you reduce the fractions. Okay, they would all be equal. So if the bottom of the first triangle is 12 inches and the bottom of the second triangle is 9 inches, I first want to find the ratio of their perimeters, which means I need to find their scale factor. Now, this one says compare the first to the second. So we're going to start with the larger triangle, and we're going to take the corresponding sides and write it as a ratio, which just means you're going to put 12 over 9, or the corresponding sides to both the bottoms of those triangles. Okay, this is going to be the scale factor, but the big thing that you're going to have to do today, you want to make sure your answer's in the simplest form. So if I reduce 12 over 9, I should get 4/3. Okay, that's the scale factor, which is convenient, because whenever I want to find the ratio of their perimeters, what would it be? Their perimeters. 4/3. It's the same thing. 4/3, same thing. Yeah. The perimeters is the same. Now, the areas, the ratio of their areas, this is where you're going to square the numerator, square the denominator. So the ratio of their areas would be 16 over 9. Okay. That's one of the things you're going to have to do in your homework today. You guys have questions on that one? Okay, this one we also have similar figures, but now we're going to actually apply this so we can help find the area. So we're going to be given the area of one, and then use the given information to find the area of the other. So number 2, we're going to have two trapezoids. We're going to have the smaller trapezoid. Over here we'll have the larger trapezoid. Okay, the top of the smaller trapezoid is 4 centimeters. The top of the larger trapezoid is 6 centimeters. And we're also going to be given that the area of the smaller trapezoid is 39 centimeters squared. The area of the smaller trapezoid is 39 centimeters squared. So what we're going to do here is we need to set up a proportion, okay? Because similar figures, their areas, okay, are going to be proportional in a certain way, okay? So I first need to find the scale factor. Now, what I said in the last one on the left-hand side, that it doesn't matter what order you go in. If you always want to do largest to smallest, great. Or if you always want to do biggest, smallest, great. I like for consistency, I just do the first one over the second one, no matter which one's bigger and which one's smaller. So for this one, I'm going to do 4 over 6. Reduce that. We should get 2 over 3. Now that's their scale factor, which means if I wanted to know anything about their perimeters, that's how you, right, that would be these ratio of their perimeters. But I'm talking about area here. What's the ratio of their areas? Squared and squared. So it'd be 4 over 9. Now remember, for this one, I'm doing smaller to larger. The entire problem needs to be smaller to larger. So we're going to set up a proportion. I already know that when I take the area of the smaller over the area of the larger, it's going to reduce to 4 over 9. So it equals, which one do I know? Do I know the smaller or do I know the larger? They tell me the smaller. So I'm going to do 39 over, I don't know the larger. That's what I'm looking for. And once you set up your proportion, we are going to use cross product. So x times 4 would be 4x. 9 times 39 gives me 351. And when you divide by 4, this says to round to the nearest whole number, it's going to be about 88 centimeters squared. So notice, normally if I wanted to find the area of that trapezoid, I would need both bases and I would need the height. I don't need that here because I know that they're similar. So you can kind of see how I can find my answer without having all the information I did previously. Okay, let's do one more of these. Okay, this time we're going to do a hexagon. That wasn't terrible. We'll do the bigger one and then the smaller one. Okay, that was better than my last class that I did. Still not great. That's better. Okay, the top of the larger one is going to be 10 meters. The top of the smaller one is going to be 7 meters. And this time we are going to have the area of the larger. And the area of the larger hexagon is going to be 259.8 meters squared. So the first thing we need to find that scale factor. Remember, it doesn't matter what order you go in, you just have to stay consistent. So for me, I'm just doing the first to the second. So the scale factor is 10 to 7. That can't be reduced, so you just leave it as 10 to 7. Remember, that is the scale factor for the side legs. It is also the ratio of the perimeters. So how would I find the ratio of the areas? Square them. 10 squared, 7 squared, 100 over 49. Now for this problem, since I did first to second, it's actually bigger to smaller. So on the other side of my proportion, which area do I know? I know the bigger. So where is that 259.8 going to go? Right? The 10 is the bigger, right? And I put the 10 in the numerator. So if I know the larger, that 259.8 needs to go in the numerator. Just have to stay consistent. Okay, over x. And then do the same thing. 100 times x is 100x. 49 times 259.8 gives you 12,730.2. Divide by 100 and round to the nearest whole number, we get 127 meters squared. Questions on those ones? Okay, and then the last thing we're going to do is we are going to be given some information. We want to find the scale factor and the ratio of the perimeters. So, number 4, here's the information we're given. We have 2 regular octagons. 2 regular octagons with areas 4 feet squared and 16 feet squared. 2 regular octagons with area 4 feet squared and 16 feet squared. So what I want to do is I want to find their scale factor, which means from this one to this one, what is the ratio of their side lengths? So let's start by writing a ratio. So the 2 numbers I have, 4 and 16. So if I do 4 over 16, keep in mind that that is the ratio of their areas. So I'm kind of going backwards from what I did for the last ones, right? On the last ones, I had their scale factor. And to get from the scale factor to the ratio of their areas, what did I do? To get from the scale factor, you squared them, right? You squared the scale factors, and you get the ratio of their areas. So if you have the ratio of their areas, how can I get back to the scale factors? Yeah, take the square root of them. So the square root of 4 is 2, the square root of 16 is 4, and like all of our answers, everywhere we want to reduce and we get 1 over 2. So the scale factor is 1 to 2. What's the ratio of their perimeters? Yeah, 1 to 2. Same thing. Okay, let's do 1 more of those. So number 5, we have 2 equilateral triangles. 2 equilateral triangles with areas 16 square roots of 3 feet squared and the square root of 3 feet squared. So this one I think just looks super complicated, but it's actually really easy. Do the same thing. I need to start with a ratio. So let's take our 2 numbers, write them as ratios. So 16 square roots of 3 over the square root of 3. What I would probably do, I'd go ahead and reduce that, right? 16 square roots of 3 over the square root of 3, what happens there? Yeah, okay, it's just going to be 16 over 1. And I love that you said over 1 because this is a ratio. You have to have that over 1. A ratio is a comparison of 2 numbers. You have to have the 16 and you have to have the 1. Now, I reduced the ratio of the areas. Keep in mind, what I'm looking for is the scale factor. So how do I get from the ratio of their areas to the scale factor? Take the square root. So we get 4 to 1, which means the ratio of their perimeters also